Cambering. What is camber? Camber is known as having a slight arc or bend induced in the beam, on purpose that is. A positive camber is when there's a rolling hump going from one end to middle to the other end. The two ends might be positioned a little lower than the middle. Hey, thanks for watching this video. It would help us out if you subscribed, like, and share this video. We are excited to keep sharing videos just like this one, and we're gonna keep posting them. But if you'd like to fast track this education, the Worker Efficiency app is on Android and Apple right now. You can go download it. It's $5 a month. We have all of our video training in there for fabrication, ironworker, OSHA courses, etc. The app also does so much in regards to financial tracking, certification tracking, upskilling, training. It's pretty cool. We put a lot of work, a lot of effort into making this app really, really great. And it would support us if you go download it. $5, okay? Anyways, we'll keep posting videos. Have a good day. We'll see you on the next one. Or have this frown look to it. Why is camber purposely induced into steel? Well, camber is induced into steel that supports or carries large loads over a wide span. Steel that supports roof, decks, and for this case, the W21x50 steel we cut, this beam assembly will be used in the portions of the second, third, and fourth floors of our office building. It connects to one of our main columns, spanning and connecting to a panel embed approximately 40 feet, 7 1/8 inches. The engineer wants to keep the structure as light as possible, and when using lighter steel material, camber is induced to give our assembly steel extra strength to support the load above it. As an example, for our W21x50 steel, if camber was not induced to our beam, we run the risk of having sag or negative camber in our steel for our second, third, and fourth floors. We don't want a saggy building now, that sounds very sketchy. These beams are supporting sheet metal, rebar, concrete, and so forth for each floor. There's going to be a lot of weight bearing down on these beams. It is the engineer's job to calculate how much camber or bend needs to be induced in your steel. There should never be any guesswork here. Your shop drawings will always indicate which assemblies need camber. For example, for our assembly 22-2A, which we have used as an example for cutting and hole making, indicates camber in its bill of materials description section of the drawings. Description for our W steel, W21x50, and then C or camber, 1 1/4 inches of camber that needs to be induced into our beam. Camber is also indicated under the drawing title, next to reference saying camber equals 1 1/4 inches of camber. What does 1 1/4 inches of camber actually mean? If you had a plumb straight line that goes from one end of the beam to the other, at the center of the beam, you could measure 1 1/4 inches of rise or having positive camber. Again, there shouldn't be any guesswork for what steel will receive and won't receive camber, as it will be in your drawings. Remember, in cutting, in addition to our post-traceability markings for our large W-shaped steel beam for our 22-2A assembly, we marked a T onto the side designated to be our top of steel. Well, now we are going to camber our assembly beam 22-2A, according to our drawings, which will camber 1 1/4 inches per our drawing directions, having the T being the direction of positive camber. Camber, like cutting and hole making, is part of our production line or beam line process. There are two main processes used to induce or reduce camber into steel, and they are cold cambering and cambering using heat. However, cambering using heat nowadays is not as common. Cambering using heat is very labor intensive and takes much longer, where cold cambering can take minutes with a special cambering press or camber pit. Heat cambering could take hours. Cold cambering is when you use force, typically from a hydraulic press, to push on steel. Special camber machines can have 2 or 3 rams that push against our steel. When cambering cold, the rams may push or deflect the steel 2 or 3 times the amount of the intended camber. While holding that hit or push, the steel undergoes a restructuring at a molecular level. When the rams are retracted, easing off pressure, the beam will then have induced camber, deflection, or simply bend. The way we hit or camber steel depends on the length and size of the steel. Where a W21x50 by 20 foot beam might only need to be pushed by 2 rams spaced at the thirds of the beam once to induce 1 1/4 inches of camber, a W21x50 by 41 foot beam, like our main member going into our beam assembly 22-2A, may be pushed in 3 spots to induce camber correctly to reach 1 1/4 inches of camber. When cambering, it's best to work within increments to get to the designated camber per our drawings. Not all camber machines are computer calibrated to give us exactly what we need. It really can be a finesse job that takes time and experience to get good at. For a 41-foot beam like ours, we could start from the center, push potentially 3 and 3.5 inches to get 1/2 inches of camber gain at the center. Then we would move to what we call the left-hand third of the beam, push it to get 7/16 of an inch of camber gain there, and then move to the right-hand third to get another 7/16 of an inch of camber gain, roughly giving us 1.25 inches of camber. Tolerances in steel construction are around that 3/4 of an inch of camber over designated camber. So with that camber being designated at 1.25 inches, as long as we are not under that number or over that number by 3/4 of an inch, we are within tolerance. However, always check with your job's tolerances for these types of things. If you go beyond 3/4 of an inch, then you have some rework. There are also other techniques to induce rolling camber. You start with the left-hand third, push 7/16 of an inch for camber gain, move to the right-hand third, push for another 7/16 of camber gain, then move to the center and push for 1/2 inch of camber gain. When steel is being held under pressure, you might see experienced guys take a mallet or hammer and hit the steel all the way up and down the steel flange. Hitting the steel under pressure relaxes the molecular structure of the steel under pressure. So when you relax the steel into camber, you get a smoother rolling camber. Push in increments. Check camber, then push again. It's especially important to hit or push lightly, especially with smaller steel beams like W12 by 25, because under too much pressure, you can actually fold the steel. We know there's a person asking about cambering using heat. Typically, this is done with a torch. You then heat wedge-shaped segments at intervals along the length of the beam. As those wedge sections cool, the beam will actually start to bend. You induce as much camber as needed for the job as evenly as possible. Cambering, like welding, just takes a lot of time and practice to get good at. Camber is definitely not something that should be overlooked as well, as it is a critical part of the fabrication process to assure buildings are built to standard, avoiding any potential for floor sag. That is camber. Again, thanks for watching. Go download the app. The app has so many capabilities for those in construction, manufacturing, service, and agencies at scale. Build a pipeline of skilled workers, build growth roadmaps, track skills and certifications, track estimated and actual time. There's so much in here. If you want more videos just like this, they are all there in the app, in the library. You can even broadcast your own training to your teams if you want to, all there in the app as well. Thanks again, and we'll see you on the next one.